Hey everybody, today we are going to have a look at what happens when we rotate an area under a curve about the X or the Y axes. This is sometimes called the solid of revolution. So here we go, here's a curve and it's spun around the X axis and produces this solid shape. We're going to use the process of integration to calculate the volume of the solid that is formed. I found this really cool GeoGebra simulation of the process, and it gives us a clue as to how the formula works. On the left hand side of our screen we have a curve that could be some sort of cubic function. The rotation is occurring between x equals 1 and approximately x equals 4.5. Now when we were finding areas under curves, we were dealing with rectangles. In this scenario, because we are rotating those rectangles around the x-axis, we are going to get cylinders. Now down the bottom of the screen, the left hand side of the screen, we have a slider. And it's got, in this case, it's got delta x equals 0.01. Delta x is the actual height of the cylinders. So by sliding this along, we can, here we have virtually one cylinder. Okay, sliding it back the other way, the height is decreasing, so we're fitting more cylinders under the curve. Until if we take it all the way down to delta x equals 0.1, it looks like it's a solid shape. And that's the whole idea of it, is that having an infinite number of cylinders, so we have the exact volume of the shape. Now if we rotate this around a bit, we can see the solid shape that we've formed. In this situation we have actually three axes because it's in 3 dimensions, but don't worry about this z-axis. Okay, it's a bit sensitive to rotate, but that's basically our 3-dimensional shape. Now we're going to have a look at just one cylinder. We are using the formula volume equals pi r squared h to calculate our volume of our solid of revolution. That's our starting point. Now the cylinder here is standing on its side, so the height of this is actually that distance from there to there, and that was delta x from our previous slides, delta x. Now, because this is rotated about the x-axis will go through here like this. Now, the distance from there, from the x-axis up to the outside, which is the radius, is the distance to the function. In other words, that distance from there is function x, or quite simply, we can just call it the distance y. Okay, so substituting the value of y for radius and delta x for height, we end up volume equals pi y squared delta x. Now, as we have an infinite number of cylinders, delta x will approach 0. So we can apply the limit. Limit as delta x approaches 0 of pi y squared delta x gives us the integral of pi y squared dx, and which then translates into a definite integral of volume is pi from a to b of the integral of y squared dx. Okay, let's have a look at this again. There's our formula, volume equals pi outside of the integral from a to b of y squared dx. Now, Let's do an example. Here we have find the volume of a solid revolution formed when the curve x squared plus y squared equals 9 is rotated about the x-axis between x equals 1 and x equals 3. Now, the first thing we have to do is to get y squared equals something. So all we have to do there is to subtract the x squared from the other side. So you end up with y squared equals 9 minus x squared. Now we're ready to plug that into our formula. So our formula goes volume is pi outside of a to b, integral from a to b of y squared dx. So substituting the values in, our start and end point is 1 and 3, and the y squared is 9 minus x squared. We do the integral of 9, which is 9x. We do the integral of x squared, which is x cubed over 3. Then we apply the start and end point. So the end point, 9 3 is 27, minus 27 over 3, which is 9, minus 9 1s, and minus 1/3, and it comes out to be 28 pi over 3. Now, when you're doing these, just remember, always give your answer in terms of pi, unless you're asked to give it to a certain number of decimal points, because 28 pi over 3 is the exact value. Now, example number 2. You have to find the volume of the solid formed when the line y equals 3x minus 2 is rotated about the x-axis from x equals 1 to x equals 2. So here it is here. There's your line y equals 3x minus 2, and it's rotated from 1 to 2. Gets this shape here, which is actually called a frustum. Okay, let's have a look at the solution over here. You've got y equals 3x minus 2. Our formula requires y squared, so all we have to do is square both sides. So we now plug that into our formula, 3x minus 2 all squared dx, from 2 to 1. Now, the book has done the integral using the function of a function rule. In this case, you could probably expand that out. It doesn't really matter which way you do it. It will still give you the same result. So doing the calculation, you end up with 7 pi cubic units. Now it's time to have a look at volumes about the y-axis. So basically it's the same formula, except the pronumerals change. We've got x squared instead of y squared, and we have delta y instead of delta x. So it's pretty well exactly the same process. There's only one example in the book. Let's have a look at it. We're finding the volume of the solid formed when the curve y equals x squared minus 1 is rotated about the y-axis from y equals minus 1 to y equals 3. So we have our y equals x squared minus 1. Now we want x squared, so we need to get rid of that minus 1, so we add it to the other side. So you have x squared equals y plus 1. So then all we have to do then is to plug the y plus 1 into our formula. Okay, so you end up with volume equals pi from minus 1 to 3 of y plus 1 to y. Integrating y, we get y squared over 2. Integrating 1, we get y. Then we substitute our start and end points. So 3 gives us 9 over 2 plus 3, minus 1 gives us a half minus 1, And that all simplifies down to 8 pi cubic units. And that's it.